Hello.
Good evening, sir.
Good evening to all. Can you see the screen?
Yes, sir.
Okay. Okay, so today we'll start with the design of retaining walls. I think many of still people are waiting. Shall we wait for 1 or 2 minutes?
Yes, sir.
Okay.
Yes, sir.
सर
Yes, बोलिए.
सर एक्चुअली बोलना था कि प्रैक्टिस के लिए सर वो नहीं हो पाया था, डिजाइन ऑफ एलिवेटेड वाटर.
हाँ, ओके.
थ्योरी सिर्फ हुआ था उसका. वो डिजाइन कैसे होता है एलिवेटेड वाटर टैंक और ये
डिजाइन तो बता ही रहेगा ना, वो सभी टैंक्स का वो सेम ही रहता है डिजाइन मेथड.
एक्चुअल में सर वो मॉडलिंग थी ना सर, स्टैड प्रो में मॉडलिंग के थ्रू कैसे करेंगे सर वो
हाँ,
चीज सर
वो
अभी
नहीं
मतलब
नहीं, डिजाइन तो नहीं करते, सिर्फ एनालिसिस करते हैं ना.
हाँ सर. तो वो मॉडलिंग कैसे बनेगा? जैसे सर्कुलर टैंक का तो पता है सर,
हाँ
वो ठीक है. लेकिन वो एलिवेटेड वाला अगर एक दो लेक्चर हो जाता उस पर तो अच्छा बेटर था. और इसका एसटीपी का भी सर वो.
हाँ, मैं चेक करता हूँ. आई विल चेक इट आउट. क्या हुआ है उसके हिसाब से मैं बताता हूँ. ओके.
ओके सर. एटलीस्ट कम से कम इसका एलिवेटेड का सर करवा देते हैं ज्यादा अच्छा. तो
चेक करता हूँ, मैं चेक करता हूँ. अभी वो हो जाएगा आगे. अभी सेशंस बाकी भी बीच में है ना. अगर कुछ मिस हुआ है, ऐसे लग रहा है, आपको लग रहा है कि मुझे कुछ और एडिशनल चाहिए, तो वो करेंगे अरेंज. एक वर्कशॉप करता हूँ मैं अरेंज, उस टाइम वो करेंगे कवर सब कुछ रहेगा तो मिसिंग. ओके.
उसमें सर वन क्लास ही इनफ है बस सर. थोड़ा स्टैड में जैसे सर्कुलर का तो बता दिया था ग्राउंड लेवल पे.
ओके.
एलिवेटेड में फिर सर वो कॉलम के थ्रू सर्कुलर मॉडलिंग करके एनालाइज करना ना, वो एक क्लास हो जाती ना सर, तो क्लियर हो जाता थोड़ा सा. डिजाइन तो सर ने पूरा बता दिया
हाँ,
सब अच्छे
डिजाइन ने
से.
बता दिया सर ने वो. तो सर क्योंकि थोड़ा कॉम्प्लिकेटेड भी है सर.
मुझे जरा स्केच भेज दीजिए व्हाट्सएप पे निकाल के, आपको क्या चाहिए नहीं क्या, सो दैट मुझे थोड़ा दिमाग में आएगा. ओके. तो
सर
क्या
वो
लेना है वो. हाँ
एक्चुअली जैसे हम लोग एलिवेटेड मॉडलिंग करते हैं ना, एलिवेटेड वाटर टैंक
हाँ,
मॉडलिंग.
ये सर. हाँ हाँ.
हाँ, तो वो कैसे करेंगे? और लोड तो हम लोग अप्लाई कर लेंगे, एनालिसिस कर लेंगे, लेकिन मॉडलिंग किस तरह करेंगे?
मॉडलिंग का क्या प्रॉब्लम आ रहा है, मुझे समझ में नहीं आया. बॉटम में स्लैब मतलब सर्कुलर का बोल रहे हैं क्या आप?
सर कोई भी एलिवेटेड वाटर टैंक कभी किए नहीं, इसलिए बोल रहा हूँ.
हाँ ठीक है, करेंगे. अरेंज वन सेशन. ओके. जो मिसिंग है ना आपका, वो करेंगे कवर. ठीक है, डाउट्स वगैरह रहेंगे तो वी विल क्लियर आउट की कैसे करना है. बाकी नॉर्मल टैंक तो आ रहा है ना आपको सभी.
हाँ हाँ, ये जो सर
हाँ
बताया
ठीक है.
है, रेक्टेंगुलर और सर्कुलर टैंक, वो हम आता है
हाँ
सर.
हाँ, तो फिर
कोई
यस सर
दिक्कत
वो तो आ गया था सर.
हाँ नहीं ठीक है, फिर ये सर इज वेरी इजी इफ यू नो दैट, मतलब पहले वाला है तो उसमें बताऊंगा मैं क्या करते हैं, और अलग अलग मॉडल्स रहेंगे तो कैसे करते हैं टैकल. ओके.
एक्चुअल में सर वो हमारी डाउट ये है, जैसे सर्कुलर जो हो गया ना, उसको फिर कॉलम पे कैसे मॉडल करेंगे एलिवेटेड में. बस ये चीज हमारे सर थोड़ा सा वो क्लियर हो जाती ना स्टैड में, तो फिर
ओके
कोई दिक्कत नहीं.
ओके ओके, चलेगा चलेगा, करेंगे क्लियर.
यस सर, थैंक यू सर.
Okay, thank you. Now we will start today design of RCC retaining wall. So can anybody tell me why we provide retaining walls, or why, what is the necessity of retaining walls? पता है क्या कुछ idea?
Sir, to hold the backfill through this retaining wall.
Yes. See,
For supporting soil laterally.
right, supporting soil laterally. So that situation comes due to the planning or our, we can say, functional requirements. For example, there may be many such situations. Sometimes, let's say this is your road level, and it may be possible that your ground level is like this. So let's say this is your ground level, and the road level is here below. And here we are having one, let's say, building like this, for example. Building or any structure, it may be industrial structure or RCC building. Okay, such kind of situation may be there, and here this soil should not go fall down on the road area. Like, so in that case, we will provide retaining wall here like this. Correct. or no, here it will be like this. Okay. So this will be retaining wall, and then the whatever this soil mass is there, this will not fall down here. So generally this triangular wedge, whatever you see here, it tries to fall down because this is your stability slope or angle of friction, we can call it as. Only this triangular soil may try to fall down, and due to that, whenever you provide any retaining wall over here, it will exert lateral pressure like this. Okay, so this is the reason why we provide a retaining wall. So this retaining wall may be required in say such kind of road level is different, and your this building level is different, the ground level of the building, or it may be something if you want to create one channel, you know that channel is created, underground channels are there, water, where the water may flow, or it may be a nala. So let's say this is your ground level, this is your ground level, and then this is, let's say, nala. Then this will be your retaining wall. So we will provide retaining wall like this. Getting? This is your retaining, and this soil, this is a soil over here. This is open area. So this soil pressure will have pressure on this wall. Okay. So you need functionally, you require such kind of level difference. So when there is a level difference of the natural ground levels or finished ground levels, so you want ground level over here and you want ground level over here. Therefore, there is a difference between the ground levels, and due to that, this soil may fall down. Okay, so this is the area. Any other example where this we require retaining walls?
So on hilly roads.
Yeah, hilly roads, right? So generally hilly roads. Okay, so if you look at this retaining wall, this is a cantilever type of retaining wall, we call it as a, okay, cantilever, or this is also cantilever retaining wall. Then second case may be in high-rise buildings, we may require basements. Let's say like this. So let's say this is your ground level and this is your underground basement, B1, B2, let's say. So that means this soil may fall down into this basement area, and we don't want that. And therefore we will provide retaining wall here, right? So the retaining wall will be like this. And definitely base slab will be there. So this is a vertical retaining wall. Now this retaining wall is having support actually. Here, there is a slab over here, you know. So there is a slab, so it will offer a propping action or support in this direction. This slab will also have a support here. And as this slab is there, there will be fixity. So if, and there is a lateral pressure like this. And due to this lateral pressure, there will be bending moment. Okay. So it will be something like this. Okay. So this kind of retaining wall, we call it as a propped cantilever. Propped cantilever. Prop means there is a support to the tops. It is a free cantilever. This there is no support here, you know. So it will behave like a cantilever in this case. So if it tries to bend, it will bend like this, right? So as it is a free end. Now here the end is not free because there is a support due to this slab. So we call it as a propped cantilever retaining wall. Okay. So such kind of retaining walls are there, and cantilever retaining wall is a we can say fundamental or classical retaining wall concept. If you understand this, then you can apply anywhere. In such kind of prop cantilever walls or basement walls, the only difference is in the analysis. So analysis, the bending moment diagrams are different, but the design procedure is same, and drawing detailing is also based on the conceptual things. So today we will learn the cantilever retaining wall analysis and design using manual calculation, we can say, so that you will understand the concepts, load path, IS code clauses, how to calculate AST and so on. Okay. So this is the way And as far as the behavior is concerned, let's try to understand the behavior of cantilever retaining wall. So if it is a cantilever retaining wall, you should know the terms also regarding this. Let's say there is a retention here. And let's say we are having some portion. So the ground level is here. And this is also your ground level. Okay. And due to this soil, there will be lateral pressure over here. So generally we call this vertical wall as a stem. This portion we call it as a hill. And this is your toe. Okay, these are the three terms. And due to this soil, there will be lateral pressure like this. Soil pressure is like this, lateral triangular pressure, more at the base and zero at the top, as it is a cantilever. Okay, and due to this pressure, and there will be due to vertical load of the soil and self-weight of the heel and toe, there will be upward pressure also, bearing pressure, similar to footings. Okay. Yeah, ऐसे रहेगा ना. Upward pressure on the heel and toe slab or bottom slab or bottom raft, we can call it as. So these are the load acting on the retaining wall. One is the lateral soil pressure. This is your lateral soil pressure, which is acting on the stem vertical wall. And there is a due to vertical loads of the soil and self-weight, there is a upward pressure, upward bearing pressure, we can say. Upward bearing pressure. Now, due to this, you understand this is a cantilever action, so the wall will try to bend like this. So you should understand the deflected shape of the any structure under loads. Then and then you can understand the behavior and tension and compression phase. So this is your bending. Now, generally this soil mass is heavy, or we can say having more downward pressure. So due to that, actually, this will also bend like this. Okay. So it will bend also like this. So this is bending like this, this is bending like this. Now this upward pressure is more. So this toe will bend like this. Okay. Getting this deflected shape? Due to this downward pressure, this will deflect or bend like this. And due to this upward pressure, this toe will deflect upward, because this upward pressure is more in this case. So it will bend upward, and this downward pressure is more in this case. So this heel will bend like this, and this lateral pressure is more. So this stem will bend like this. And therefore there will be, so there will be cracks here. So that means this is a tension phase. Then there will be crack here like this. So there is a tension at the top. And here there is a crack here. So there is a tension at the bottom. So if you see the reinforcement, then I can say the reinforcement is here. Main reinforcement is here for the toe region. And for the heel, the top will be the main reinforcement, because bottom is the compression. And in the stem, this vertical line will have a tension, main steel, and the other side will have distribution steel. So are you getting the overall behavior of the cantilever retaining wall?
Yes, sir.
Once you understand, then we will just see the process of design. It is as per the books actually. So the main important part in structural engineering is to understand the behavior only. And the other processes are same, to decide the size, to calculate the steel as per IS code clauses, then to check the shear stress or shear check, we can say. And then, so these are the only things actually in structural engineering. Once you understand, the analysis is generally difficult and rather tricky. Once you understand the analysis, design procedure is very easy. Now we are taking one example similar to this only, whatever I discussed. So let's take, okay, so let's take this example only. Here, this is the example, and see this height is 3 meters. Okay. And this is, okay, I'll show you the first picture only. Yes. So the known part is, say, given is this. In reality, if there is a road level here and building ground level over here, so 3 meter is the height. So this height is 3 meter, which we know, and we don't know anything regarding this. So whenever we design the retaining wall, only retention height is known. Other things are not known. For example, if you see this, so only I know this. What is this height? Okay. And this height is 3 meter in our case, and this is our problem. That's it. Now we want to design the retaining wall, so we need to decide this width. Then yes, we cannot put the retaining wall exactly on the ground level. So generally, whenever we put any foundation, it is below the ground. Sufficient depth is there, let's say. So it should go a little down, then it will have like this. Okay. So there is a minimum depth of foundation here. Okay. From here to here. And then we can provide the base slab or raft here. Okay. So this is the 3 meter problem statement here, and we want to design the retaining wall. So how to decide the dimension? Let's see. So these are the known all grade of concrete fine. The grade of concrete M25, grade of steel 500. Cover to the reinforcement generally we take for retaining wall 40. Then height of retention we know 3 meter is given. Unit weight 25 kilonewton per meter cube. Soil density 18 kilonewton per meter cube, and coefficient of friction of the soil 0.6. Generally we take it this. And angle of repose 30 degree, and soil bearing capacity 300 kilonewton per square meter. Okay, so this is the known. Now we need to decide the dimensions of the wall. So whenever we decide the dimension, generally minimum top dimension we take 200 mm. Okay, generally. So this dimension is clear to you now. Then overall height of the, so actually this is our 3 meter, you know. This is your 3 meter. But we need to add this minimum depth of foundation. So minimum depth of foundation we generally calculate TF is equal to Q upon sigma. Q means soil bearing capacity. 1 minus sin phi upon 1 plus sin phi bracket square. So 300 is our SBC, 18 is the density of soil, and phi is 30 degrees. So this will come out to be DF is equal to 1.85. Okay, so this dimension now we are getting 1.85. These are rough dimension. It is not necessary that you should follow exactly this. You can have more also if you feel, depending on the hard starter level. So let's say your hard starter is not at 1.85. Your SBC is 300. But if you don't get the SBC 300 at 1.85, then you can increase this DF value. It's not that you should follow only this. Either 1.85 or where the SBC is 300. The SBC may be at 2 meter, 2.25 meters. So you can increase this also. Now for this problem, let's take this minimum dimensions. So DF will be 1.85. So you got this overall height of the wall, then thickness of base slab. So this is the thickness, this one, vertical thickness. So this thickness of base slab is H upon 10 roughly we can take. See, these are only say assumed or thumb rules we can say for deciding the sizes of the retaining walls. Whenever I say thumb rule, that means the number may vary here and there to 10 to 15%. There is no problem. Instead of 485, you can think of 500. Or instead of this, we can say 4850, you can say 5 meters like that. So there's no problem. But where to start? Generally, we find difficulty to start the problem actually, because we don't know the size, we don't know anything. We only know the 3 meter dimension. So how to start? So these are the thumb rules. Then width of the base slab from here to here, roughly 0.6 H. H is now 4.85 total. So you know this 3 plus 1.85, 4.85. So 0.6 into 4.85, 2910 mm. Projection of this toe slab from here to here. Here, this projection. From this to this. B upon 3 roughly. So 970. Okay. So these are the dimensions we got. Top width 200, total height 4850, thickness of base slab 485, and width of base slab 2910. So let me show this. Let me just increase this for the time being. See this now. 200, overall height 4850, thickness of base slab, width of base slab 2910, and depth of foundation 1850. Okay. Now let's go to the next step. Now the next step is calculation of pressure, lateral pressure. So what is the lateral pressure we get? Actually, it should be here. Am I audible? Hello?
Yes, sir.
Okay. So यहाँ pressure आ रहा है हमारा. See this, because this is your height of wall. For the time being, forget this. Okay. So this is the level of pressure. So this pressure is Ka gamma H. Okay. So this base and the top is 0 and linearly it is varying. Okay. So this value is Ka gamma H means K is, now let's see, Ka gamma means gamma D. Now we are taking dry density. What is dry saturated? We have seen that in last session, I think. And this is your H4365. Okay. And this is the lateral pressure which is acting on this wall. Now let's see how to calculate that. So lateral pressure is Ka gamma H square upon 2. Or we can say how to get that. Total area will be the, see, this is the, see, if you want to calculate the area of say triangle, so PA, total pressure will be half into base. Base is how much? Ka gamma H into height. Okay, so Ka gamma H square upon 2. Getting this resultant lateral pressure. And
Yes,
where,
sir.
and where will it act? It will act at H by 3.
At H by 3.
H by 3 pe rahega. So this is H is our this 4360. So we get this lateral pressure, PA, resultant pressure, total pressure we are calculating, area of triangle. And due to this lateral pressure, there will be bending moment. Yes or no? So we have seen this. So this PA into H by 3 will be the bending moment. So this wall will try to bend. Yes. And that bending moment is nothing but PA into this H by 3. Okay. So here you can see here. So this is the PA into H by 3. Right. So PA is calculated here, H you know, and 3. And so this is the bending moment. Now this PA is working pressure actually. And whenever we design any RCC element, it may be RCC wall, beams or whatever, we design it by limit state. Okay. Limit state. So limit state means we need to multiply the load factors, ultimate moments. So 1.5 into this will be the moment. So this is your moment. Now, due to this moment will, what will be the bending moment diagram for this moment? Ye tha na mera. So due to this pressure, let me show the loading diagram. And there is a loading diagram like this. So we will have a bending moment like this. Yeah, aise rahega na bending moment. On the wall, bending moment of wall. And this is your MU, right? Which is at the base. So I want to calculate the thickness of the wall at the base because the moment is maximum at the base at this level, right? Now, how to calculate the thickness of wall at base? So you know that you need to equate that with moment of resistance, MU limiting, which is 0.133 FCKBD square is equal to our design moment, 124. You know all the parameters, only unknown is D. Small d means effective depth. So this is coming out to be 193. So total D will be 193 plus cover plus diameter by 2. So I think this is very clear to all of you. I'm just deliberately taking this on the higher side so that other checks are satisfied. So we are getting this overall depth 450 mm. Okay. Now we can calculate again D provided, total depth minus cover minus D by 2. Okay. 404. So what is the thickness of stem we got? Stem means wall. So this is our now 450. Here, see this. We got this 450, right? From here to here. Now the next step is actually generally we need to check the stability first, but okay, let's see the process. Now once you know the depth, then you can you know the moment mu, you know the depth, then you can calculate the AST. You know the formula for AST. This for put all the values: grade of steel, concrete, mu, B and D. B generally retaining wall we design it for 1 meter width or 1 meter length, we can say. Okay, it is similar to slabs because the retaining wall is very long. Even though you see this section, actually the retaining wall is like this, long retaining wall. It may be 10 meter, 50 meter, whatever. And we are only designing for this 1 meter portion. So 1 meter means this dimension is 1 meter. Okay, try to understand what is that 1 meter or 1000 mm. This is your long retaining wall. I am just taking 1 meter length of the wall. Getting? So we are designing for 1 meter only. And once you design for 1 meter, you can apply the steel for whole length. So that's why I'm putting one is B is equal to 1000, then D square, and I'm getting this AST. Okay. Now let's assume some bars where what you want to put. 12 mm diameter. You know how to calculate the spacing of the bars. Small AST divided by capital AST, which is this. And finally, you get this spacing of the bars. So 12 mm at 125. So where you will provide this steel? ये stem का steel कहाँ provide करेंगे? 12 at 125. So this one, yeah, this right line, right? This is your that value.
Yes, sir.
Yeah. Now there is one more check. Don't forget that whenever you calculate the AST from the design requirement, you need to check the minimum AST also. And minimum AST is 0.12% of gross area of the wall. 0.12 upon 100. This is B and this is D. Now D is varying actually in our case because it is a trapezoidal thickness. This width is different and this width is different, right? So we will take the average. This is 450 and this is 200, and that's why in the calculation we are taking this 200 plus 450 divided by 2, average thickness we can say. And this is the AST minimum. Okay, so your this value is more than AST minimum. Okay, that's why we will provide for 737 only. Now where you will provide the minimum steel? Let's assume the diameter of the bar as 8 divided by AST minimum here, this one and this. So we are getting 8 mm T8 at 125 as a minimum steel. Okay, so where you will provide the minimum steel? Wherever there is no requirement of any steel, right? So समझो ये वाला, this is a compression zone, yes or no? This steel.
Yes, sir.
So this will be my minimum steel, AST minimum, which is 8 at 125 center to center, because there is a compression zone. Now there are distribution steel also like this, yes or no? Is there any force in the distribution steel? क्योंकि ये ऐसे bend नहीं हो रहा ना, horizontally it is not bending. As it is not bending in horizontal, so these dots are also only AST minimum. Correct? Getting? This distribution steel we can say.
Yes,
So
sir.
distribution steel will be minimum steel. Only this red vertical internal will be our 12 at I think 125 main steel. So this is the design of stem or wall we can say. As far as steel is concerned, now there are other checks. Development length calculations, I think all of you know LD is equal to 0.87 Fy into diameter divided by 4 tau BD. Generally,
Yes,
so ये तो पता है आपको 0.87 500 diameter, tau BD ये value है 1.4, and you need to increase this tau BD values also for Tor steels. by 1.6. So this comes out to be 600. So generally, you know that your LD is generally 55 to 65. Yes.
Yes, sir.
So 55 किया तो 12 into 50 will be 600. तो ये आ रहा है लगभग, right?
Yes,
So generally these are the LD values we use in practice, but the calculation basis is this. So LD calculations, now there is a shear check. Now where to check the shear? So generally shear we check at the D distance. So all of you know that shear हम D distance पे लेते हैं. So let's say if you, this is your wall. So I will take the shear check at this point. अरे यहाँ क्या? If the wall is there, then we take the shear check at here somewhere. Huh? And this distance is small d, at a distance d. Then if this hill or base slab is there, in this case, we check the shear check here. Okay. Try to understand where we are taking the check shear. And then for the toe also, we are taking the shear check at distance d. Are you getting where we are checking the shear check? Stem के लिए यहाँ है, heel के लिए यहाँ है, and for toe it is here, right?
Yes, sir.
Okay. So please try to understand the location of the shear check. Huh? And that means you know that you need to, so whenever you calculate the shear force, you will calculate till this point only. Okay, this point, not below that. So let's see how to calculate. And now we are currently we are doing this stem design. So what is this? So unit. So how to calculate? You need to calculate this. You know D provided. So you can subtract this. ये हमारा कितना है 4365 minus this D will be this height of the triangle. This one. Then it's very easy actually. And then you can get that. So this K gamma H. So you know this will be K gamma H. H will be this. H, let's say revised. HR, this one. After subtracting this D. And then you know how to calculate the horizontal force. This is PA will be the shear force, right? Yes, so K gamma H square upon 2 into 1.5 because of ultimate shear, ultimate. I think you are getting this because it's very easy.
Yes,
so this
sir.
is your shear force. Then shear stress will be V upon BD. B, you know, 1 meter we are taking. D is the D provided. 0.17 Newton per mm square here. And permissible shear stress we calculate from the table 19 of the IS 456, which depends on the percentage steel. So 100 AST upon BD. 100 AST will be the AST provided. So AST provided is 904. Where we have provided the AST? Here. AST provided, right? So there it is. We are taking the 12 mm at 125 upon BD. So 0.22%. So from the interpolation from this table, we get the tau C value as 0.336. And that means tau C is more, permissible stress is more than the actual stress. So that's why it is safe. So generally in retaining walls, the shear check is satisfied generally, similar to slabs. So we need not to design any shear retaining wall for shear actually. But yes, for the curiosity or for the process of design, you should follow this. Now, actually, this step should be first. I've given here 5, but actually stability check must be taken first. So before the design of even wall. Let's see. Now, how you know, if you look at the retaining wall, so what do you think? How will it fail? Why it will fail and how will it fail? Fail or collapse, I would say. Collapse is something different and fail is something different. Fail may be design failure, and collapse means it is a stability failure. Do you know collapse means? If the structure is not stable, then it collapse. It will collapse. Huh? Unstable structure. So you know that there is a lateral pressure over here due to the soil. And what will happen? This lateral pressure, due to this lateral pressure, this wall will try to rotate or overturn about this point. It will be something like this. It will overturn. Yes or no? Is it convinced? Hello?
Yes, sir.
Yeah, so it will overturn. So overturn, that means you should check the wall for overturning. That means wall should not overturn. So overturning is one of the stability parameter. And second is due to this lateral pressure, you know that there is a lateral pressure here on the wall. This wall may slide also. It may slide due to the lateral pressure, because if the friction between the wall or the sliding force is more, sliding force is nothing but this force. Huh? This PA is nothing but this wall will try to push the wall here in the horizontal and it will slide. So there is a sliding check. So these are the two checks for stability checks. So before designing any wall or slab, you first check the stability and then you can go for the design, because we cannot analyze and design the unstable structure. So first it should be stable. So how can I may say that it will be stable? So you see here, once the force is applied and it doesn't overturn, then what will happen? It will not overturn, but it may bend. So there is a difference in stability and bending or deflection. Please try to understand. Now let's say this is your stable structure. So you have taken care that it is a stable. And now there is a horizontal pressure, you know. Now what will happen to this? It is stable, but it may bend. So whenever I say it may bend, that means, see, it is deflecting or bending like this. It is also deflecting or bending like this. That means this point is now working as a fixed support or anchored here. That means it is made such a way that this will not overturn like this. Okay. But yes, it may bend. That means this is my stable structure. I can analyze, I can calculate the bending moments, and I can design the structure like this. Okay. So how to check this overturning and sliding? Let's see. So in this, now tell me, yeah. So who is causing the overturning and who is stabilizing this? I mean, why it is overturning? Due to this lateral pressure, right? And where it is overturning? About this point. If it overturns, where will it overturn? About this point. And that overturning is due to this PA into this distance, whatever may be the distance, PA into X. So overturning moment will be PA into X. PA is the horizontal resultant force. Now, if the structure wants to be stable, if you want to avoid this overturning, who is resisting this overturning moment, or who is stabilizing this moment? So
Sir, weight of the structure.
Yes. So there is a weight of the soil over here. Then there is a weight of the base slab over here, or hill slab. And there is a, okay, toe will not have much, but okay, there will be like this. And this stem weight is also there, right? And about this point, then let's say this is your, let me say what, W1, W2, I don't know, before study. So who will stabilize? Overturning moment, you know this, PA into vertical X, H, let's say small h. So overturning moment is PA into H, and resisting moment or stabilizing moment is this W into this distance, CG of this rectangle. Then W2 into this distance, CG of the base slab, and W4 into this distance. Are you getting this? And W3 into this distance. From overturning point, we will measure the centroid of all the rectangles, and that will be summation of all the moments, will be the resisting moment. Okay, so we will see how we have calculated that. Then this, see, this is W1, W4, sorry, now in this W4 for this base slab, it is W3, and W1 for this rectangular portion of the wall, and W2 for triangular portion of the wall. And PA is the horizontal resultant force. So W1, how to calculate? W1 matlab kya hai? So this rectangle, width into height into density into 1 meter.
Yes, sir.
Width into height into 1 meter into density. That is the total weight of the rectangular wall. Then W2 means triangular wall weight. So you know half into base into height. W3 is the weight of the base slab. So you know this 2910 into thickness of the base slab into 18. And okay. Now W4 is, I think, soil pressure. So W3 we have seen. W3 is the base slab weight. And W4 is the soil weight here, this soil weight. So this width into height into density of soil, you know, it is 18. And there is a triangular portion also, don't forget here. यहाँ ये soil का triangular portion भी. This portion is the soil. So for that also we have calculated the weight. This one half into base into height. Okay. So the total downward weight will be W1 plus 2, 3, 4 will be 197. Now what is the centroid values? X1. X1 is for W1. So this W1 is there. I'll show you here. Now tell me, X1, you see this. This is your point of rotation or overturning. This is your X1, the distance of CG from this point. Then what is X2 for this triangle? So ये क्या आएगा यहाँ? H width upon 3 plus this distance. Okay. So this is actually geometry. You know how to calculate the centroid of any rectangle or triangle. So in this fashion, you can calculate the centroid and then you can calculate the resisting moment. So X1, X2, X3, X4 are calculated here. And finally, the total moment will be summation of all the moments. These are the resisting moment W1, 2, 3, 4 into this and minus PA. So let me show here again. So you know this into X1, then this into X2. See this one. W1 into X1, W2, X2, W3, X3, all summation will be the resisting moment minus horizontal force into H by 3. So total moment will be how much? 283. Okay. Now there is a second check here. X bar moment of summate total moment divided by total weight will be 1.4. Generally we calculate the eccentricity. Eccentricity is B upon 2 minus X bar. X bar, you know, total moment divided by total weight. And you calculate the E by this formula. You get this E. And for no tension. So actually there should not be any tension in the retaining wall. Retaining wall means soil. Tension in the soil. So try to understand. No tension means no tension in the soil. So E should be less than or equal to B by 2. So it should be B by 6. Okay, so 2.91 divided by 6, so 0.485. So your E is 0.015 less than this, so it is okay. Now this was the check for no tension condition in the soil. Second is the overturning check. So this clause is given in the IS 456.9 MR. MR means resisting moment or stabilizing moment. MO is overturning moment. So what is MO? You know, PA into H by 3, horizontal force into this height. And resisting moment W1, X1 and all this summation of all the forces. So it is coming out to be 361. This is 83.9 into MR divided by this. So the overturning factor of safety is 1.2. This is factor of safety as per the code. So it should be, your factor of safety should be more than this 1.2. Then sliding check. Sliding check also, frictional force upon horizontal force should be greater than 1.4. So what is the frictional force? I think all of you know how to calculate the frictional force. समझो ऐसे एक block है rectangular समझो. And there is a horizontal force. So, and there is a weight of the block downward, right? So who is resisting this? If this block tries to move horizontally, there will be friction, right? Yes or no? Within this joint.
Yes,
So
sir.
that frictional force will be mu into W, right? Mu is the frictional coefficient into W. That will resist this. Now this is nothing but we are calculating this. This F is nothing but our frictional force, which is mu into 0.9 into W, summation of W, which is this. And overturning, say horizontal force PA we have already calculated for walls. So the ratio is 1.4, more than 1.4, which is safe. Now check for crushing means bearing pressure, we can say. It is not crushing, let's say. Check for bearing pressure or soil bearing capacity. You know that due to the moment and axial load in footing, you have seen that, right? See, there is a pressure like this due to this moment. So there is a vertical load downward due to the soil, due to the weight of the heel and everything. So there will be P upon A. This pressure will be on soil, pressure on soil. And due to this moment, overturning moment also, there will be plus or minus M upon Z. All right. So this is your bearing pressure on the soil. And that value should be less than SBC. Yes or no? So there are two pressures. One is the sigma will be P upon A plus M upon Z. Whatever value it comes, it should be less than SBC. There is second case, P upon A minus M upon Z. It should be more than 0. So there should not be any tension, no tension. Correct? This is the simpler understanding, and now we will see. The books have developed this formula, sigma max. So I have shown that sigma max. First one was the sigma max, and this is sigma min. So sigma max is, they are just doing this. Z is, you know that Z is what? Z is BD square upon 6. Yes. So they are rearranging the formula, and they have developed this final formula. Okay. So sigma W upon B, this formula. So sigma max will be 70 and it should be less than SBC. So here it is less than SBC, and then sigma W1 minus sigma means should be more than 0, no tension condition. So stability is satisfied now. I think it is clear till now.
Yes, sir.
So stability check is done. Now let's go for the analysis and design of the base slab. Right. Mute करे कोई तो on है क्या? Okay. So now we have calculated the sigma max here. You can see the pressure at the base. Whenever I say this is nothing but the pressure in the soil. Huh? Sigma max, sigma mean we have calculated here in the stability check over 70 and 65.82. Okay. And you know this horizontal force also. So there is a K gamma H over here. Huh? K gamma H, which is required for our this calculation at this level. Now, You have all the forces in the diagram. Now, if you see this right portion, अभी पहले टो लिया है क्या? Okay, टो देंगे. So toe में you see this is the portion which is upward, which will try to deflect this toe like this, right? So the pressure on this toe is this. So if I consider this toe as a fixed cantilever like this, so let's say this is your toe dimension 970. Here 970 है आपका, this fixed. And what is the pressure coming on the toe? Yeah, this is like this. This portion, this only zone. And this will bend that. Yes, a bending always. So you can calculate these pressures through interpolation, because you know this is a 70 total. You know this is 65. Then you can do the triangle and rectangles and you can calculate these pressures. And finally you can calculate the bending moment. So you see this is given here 970 and 485. And yes, on the toe, don't forget that there is a downward pressure also here, right? So there is upward pressure due to this soil bearing pressure and downward pressure due to this soil mass. So WT and then U1, U2 is the upward pressure, and due to this upward pressure, there will be bending moment, this MT, right? So how to calculate bending moments? Very easy. This U1 into this distance, then U2 into this distance, minus WT into XT. You can read this. We will share this document to you. Understand the concepts, the calculations, you just can read, no problem. So moment is this, and once you know the moment, you can design it. So first of all, let's calculate the moments. This is for toe. Let's calculate the moment on hill. So hill, who will cause the moments? So this pressure diagram here, this one. Similar to toe only, but in this case, the downward pressure is more. So W4 into this X, whatever distance is there. Then toe and then upward pressure. So once you do the calculation, you will see that the downward pressure is more, and that's why it will bend like this. So, and that moment, let's calculate. So here you can see hill slab, WH 1, 2, 3, 4, U2, here it is given. And finally, we are getting the moment HU as 51. Tension at the top, because it is deflecting downward. Now, how to calculate the depth required? You know, moment of resistance into moment, design moment. So you take the maximum of the toe and base slab, because both are same actually, right? Toe and base, I want same thickness, right? So that's why I will take the maximum moment out of this heel and toe, and where I will equate this and I will calculate the D. So all other formula are same. Then calculate the AST minimum by this 0.12% of the width into thickness of, it should not be wall, it should be base slab. Then AST minimum, then AST design will be by this formula, and finally you will provide the maximum of the two. So actually in this case, AST minimum is governing. So let's assume 12 mm diameter. So calculate the spacing of the bars. See, I'm not going in detail because you have already learned this, how to calculate AST and all this. Distribution steel 0.12%, again the same. You can use maybe 10 mm diameter, and 10 mm 125 will be the steel. Then we calculate the provided steel also, because it is required for the shear check. Then heel slab calculation, same process, AST minimum, AST design for heel. And distribution steel, again same thing. And then we can check the shear. Now, I've already told you that toe slab, the critical section is at a distance D. Here we have seen where to check this. Critical sections, this one. This is your toe, so it will be at a distance D. So in this, what will happen whenever you calculate the pressure, you know, this is your diagram. So here you will take only this zone. This area of this diagram will be the shear force, which is given here. This one. Here also, till this point, let me delete this now. Now I know that this will be my shear location. So this will be my, and this is the area of this diagram will be the shear force. So how to calculate this ordinate by interpolation? You can calculate. And finally you get this. Actually, this is by interpolation, and shear force will be the area of the diagram, which is 55 kilonewton. Then shear stress V upon BD. Then PT, percentage steel provided in the base toe. And finally, using this interpolation, you can check whether tau C is greater than design moment. Okay, it is safe. Hill slab, the critical section is at the face of the support. Okay. Same thing. Only it is at the face. So here itself. So the total diagram area will be this at this point. This is your shear location. Calculate that by interpolation and then check the stresses VU upon BD and actually tau C greater than tau V. Okay, so this is the hill. You know these tables, table 19 in 456, AST minimum, and this is your final diagram. Correct. So here you will see that this is your main steel, correct? Which is T12 at 125, and whenever you do that main steel, it should go down like this, and there it should go from here to here. It should be LD. Okay, minimum LD. So if it is a 12 mm diameter, then how much it should be? It should be something 600. We have already calculated, right? Currently, we have given little more. You can take either how much it is 485 minus cover. So let's say 400 plus 200. So this can be 300 also, or you can provide more also like this. Okay. So this is the LD. And this is the main steel. All other steels are AST minimum 8 at 125, this 8 at 125 distribution steel dots, and even vertical steel also 8 at 125. Only this is the main steel. Because the tension phase is this. I hope you got this. Now, second point is the hill slab and toe slab. So we have calculated this is coming out to be 12 at 125, 12 at 100, I think. So this is your 12 at 100. Now, we generally don't separate out the heel and toe, because what happens, generally toe dimension is very less. So it is better to continue these bars till the end. So from this to this end, and then make it L here and L here. Okay. So we don't separate out this steel, just keep it ahead. Now for the toe, whatever steel is coming, we will continue in the hill slab. Because this dimension is generally very small, 1 meter, 750, 800, or no need to unnecessarily complicate the design. And then these dots are nothing but your distribution steel, 10 at 125. Okay. This L is important and this L is important. So the critical point in the design. These two dots, if you want to avoid, you can avoid also. There is no actually reason for providing these two dots. Okay. There is one more point. You need to provide the weep holes. So generally, if there is no problem here, let's say it is a road area or there is no structure in this zone, then you can provide the weep holes so that there will not be any water pressure. So currently we have designed the retaining wall for only soil pressure. Yes. No. This is only soil pressure, which is gamma D, K gamma DH. So, but during the rain, there is a possibility that there will be water here, and then there will be additional water pressure here, gamma W into H. So if you don't provide these weep holes, then add the pressure gamma W into H. Gamma W, you know, it is 10 into H, whatever H is there. K, you can calculate by formula. Dry density is 18 into H. And if you don't want to create any water pressure in this retaining wall, then you can provide holes so that water will go down. Okay, go outside, and the pressure will be released for the waters. In that case, even for the safer approach, because in rainy season, definitely the soil will be saturated. So this gamma D, instead of that, you can think of providing gamma saturated also, which is gamma D is 18, you know, and gamma saturated is 20 kilonewton per meter. So such kind of conservative approach can be taken because it is more practical, I think. Now the process of designing of retaining wall is easy actually. Once you understand this, then now the problem may be there regarding the practical issues or some different issues like this. So as I told you, if there is a water here, then you need to design for the water pressure. And if you want to release the water pressure, provide this kind of holes. Now there is a other way of, so second problem maybe I can think that as I told you, the retaining wall is there, but there is a prop. So there is a slab over here, like you know that you have designed the water tank, so you may be knowing that. Let's say there is a retaining wall like this. But yes, there is a slab also here, maybe due to the building. Now in this case, the philosophy is same, or the pressures are same, forces are same. The only boundary condition is changing. Instead of free, it is now propped. Or propped, we can assume as a generally, I assume simply supported. So I can say if I draw the loading diagram of this structure, then it will be fixed at the base, and there is a pinned, or better to show like this. Then we have a pressure here like this. And we will have a bending moment diagram. So the pressure is from here, so the negative moment will be here. So it will be like this, okay? For pure cantilever, it was only in this side only. So if this is the case, so we get this moment, let's say hogging moment here and sagging moment here, positive, negative, whatever. So you need, now there is a tension in this face also. Now the main steel in this case will be here also. So this steel, inside steel, you will design for MH, and this outside vertical steel you will design for
MS.
MS. Okay, and the dots will be distribution steel. There's no problem. So such kind of, now the problem, or rather the difference is only in the boundary condition, and due to that the analysis is changing, moments are changing, right? But all other design philosophy is same. Calculate moment of resistance, AST minimum, AST 0.5 FCK formula, then shear check, everything is same. The only analysis is different. So many times in structural engineering, actually design is easy. The more important thing as a structural engineer is to decide the boundary conditions, then to analyze as per the boundary conditions, to design as per the analysis, and to detail as per the to detail the reinforcement as per the assumptions done at every phase. So that is the critical point. So if you see this, now we know that this vertical steel, I have taken the only distribution for this. But if it is a propped, then this will be designed steel, whatever comes from the analysis. So this is also one case where you can do this. Second case may be, I told you, I think previously, when there are basements. Two basements are there, then you can draw the loading diagram like this. This is fixed one. There is one prop over here, one prop over here. And there is a triangular load. And due to that, there will be bending moment like this, something maybe here is. Okay, if you assume this as a simply supported at this end. So this will be now, there is a MH1, MH2, MS1, MS2. You can take, you can even what curtailment you can also do, optimize the steel also. And if you don't want to optimize the steel, then you take the maximum of these two, MS1 and MS2, maximum of MS1 or MS2 for this steel, this side steel. And for this side steel, you take maximum of MH1 and MH2. It's up to you. Or if you want to curtail as per the floor height, you can curtail also. Design this floor for these forces and design this floor for these forces. Generally, value engineering or optimization can be done this way. As a beginner, you can think that you will go for the conservative or safer approach. But as you get the experience, or if you have any superior to monitor your calculations, then you can optimize the steel also. So this is one case in retaining walls. Then what else we get? Okay, so any questions?
Sir,
बोलिए.
sir, in case of sliding, if it fails the criteria of sliding, we can provide a shear key also. I have
Yes,
read,
yes, shear key. Yeah,
somewhere.
shear key you can provide. Yes, you can provide shear key like this. It will be something like this. You can provide. Yes,
Yes, sir.
you can provide the shear key. So whenever you calculate the resistance, abhi yahan resistance you have calculated the mu u into W, right? Frictional resistance. There will be additional resistance. Ye wala. Okay. There is a lateral pressure, isn't it? So this will be passive pressure, and passive pressure will be K P gamma H. Okay.
Yes, sir.
So from here you can take this height, and calculate that P frictional resistance due to passive pressure, let's say. And you can add that in your calculations. Getting? Kar sakte hain
Yes,
aise.
sir.
And then detailing also has to be done properly, once you understand the design philosophies, design procedures, the main focus must be on the drawings and detailing. Don't forget, because finally those drawings are important. If you don't do the detailing correctly, then your analysis and design has no value. The shear key you can detail out like beams also. So different consultants are using different philosophies, but the overall design is, so you can provide like this also, like beams. You can provide like beams, and then you will provide the dots here. This way also you can detail out with this side face. Or there is a one way, other possibility is, okay, let me draw this first. This is your top steel, this is your bottom steel with EL. And you can provide U bars also, U bars, I think. Do you know what is U bar? U bar is like this. U bar is like this. No need to provide the stirrups, but just this one. And then dots. This way also you can do. But you must make sure that this total depth is LD. Okay. This should be LD from here to here. And if the LD is not satisfied due to vertical, then you can do EL like this. correct? So if there is no sufficient LD, then you can provide LD like this plus this. So these are the detailings of the shear key. Yes, any questions?
No question, sir.
Okay. So practice on this. See, first of all, develop your procedure of the design first, and then think of the different problems which are practical. And if you have any practical problems, share with me. I will give you the solutions. See, solutions, whenever I give the solutions, it is my opinion, but there may be many solutions for the same problem. So try to understand. There will be exchange of thoughts. Now, I hope that many of you have already joined the training course, and I think design thought process is clear to all of you. Only now we will have a discussion with respect to the practical problems and different opinions, we can say. So those who are freshers, I don't know, there may be some freshers, but those who are now quite old, I think from B1 batches are there actually people. So they can ask me any questions regarding the practical issues also, maybe on the technical forum group. Okay. So if the questions are over, then we can close today's session.
Hello, sir.
Hello. Yes, Poli.
Sir, one question. Is there any
Yeah.
limitation of height for the cantilever retaining wall?
Yeah, quite good question. Okay, this cantilever retaining wall, I would say that you can go till 4 to 5 meters. Okay, 5 meters, let's say. Even people go for 6 meters or 7 meters also, but 5 meters or max, I would say 5 to 6 meters max. Because as the height goes on increasing, the thickness will be increased, steel will be increased, and the overall cost of the retaining wall will be increased. In that case, generally we can provide counterforts. Okay, so such kind of counterforts may be there, like this. Then the overall bending moment gets reduced. Counterforts, all of you know counterforts. What is counterfort?
Yes, sir.
Counterforts, if this is a retaining wall, let's say in plan I'm showing. If this is a retaining wall in plan, then we generally provide such kind of counterforts. In plan, I'm just showing in plan. Fine. Now, in this case, the bending is not vertical only, but there is a horizontal bending also, like we say water tanks, we can say. So the section is same. Let's say this is your section. Okay. In this case, between these two counterforts are acting as a supports. So if I draw the loading diagram, so the counterfort is nothing but your support like this, props or supports, whatever. And you know that there is a soil pressure, which is, let's say, coming from here. So soil pressure is here like this. So it is better I will show the props in different direction actually, so that it will be sensible. So these are the props. And there is a horizontal pressure here like this, due to the soil pressure, we can say. And then there will be bending moments. Continuous beam, similar to continuous beam. There is no other. Okay. So this is the horizon. So that means you can say that definitely it will have a vertical bending moment also, but not for 6 meter height. Maybe some generally h/3 we take roughly. And if you want to go for detail, then you can go for the stat analysis for this. But roughly as a manual calculation, h/3 is a good number, which you can calculate for this vertical moment. And you will provide the steel over here, right? For vertical moment. Now horizontal moment you can see here. This is the horizontal moment inside. MI, let me say MI. This is your M outside. So whatever MI is there, it is a horizontal moment, right? That means MI, I will design here in the form of dots. This is the, I will calculate the steel, and this steel I am calculating for MI, inside moments, horizontal moments. MHI, let's say MHI, horizontal moments. And M outside will be these dots. These dots are M outside. Now, what have you done? Instead of having a full vertical cantilever of 6 meters, we have given these supports like counterforts. And due to the counterforts, the behavior got changed. So instead of full vertical moment, now it is a partly vertical moment till this height, let's say h/3, and partly horizontal moment like this. So we have distributed the load path in such a way that the behavior got changed. The forces got, we can say, distributed in all directions. Previously, what was happening? Only there was a vertical bending moment like this and deflection like this. Now it will deflect horizontally also. So the wall will deflect something like कैसे होगा ये? Similar to bending moment, almost, right? So this is your bend deflection. In cantilever wall, what is happening? Do you find any horizontal deflection in cantilever walls? In
No.
plan, ये bend नहीं होता ना, पूरा wall
No.
ऐसे deflect होगा. So now this is the way we can control this. Now then you can go for 7 meters, 8 meters also. And for larger height, again 8 meters, 9, 10 meters, then there are actually special walls actually. People are designing like, I think, what kind of, in bridges the people are using the geotextile.
wall.
Ari wall, but they are providing, so I will show you the concept, but I have not designed that so much of heavy walls. The bridge, they are required in bridge generally, not in other structures. So what they do, all of you know that why the retaining wall is getting deflected due to this. There is a shear plane here, and due to that, this soil mass is exerting pressure on the wall, and that's why there is a lateral pressure of the soil on the wall. You know this. Now, what they do in that, generally they provide that geotextiles here in the horizontal directions. Geotextile means it's kind of prop, we can say. So this kind of geotextile will be there at certain height. What happens due to this geotextile? You see, this plane gets cut over here. And due to that, whatever I am saying, the horizontal pressure, it gets converted into the downward pressure, right? So instead of horizontal force, it will have a vertical. That means this load is going directly downward. Similar to here, you know, in this zone it is downward, but after this shear plane, it is a horizontal generally. But if you provide these geotextiles, then it will go downward. And so there will not be any pressure on the wall. And due to that, the thickness of wall is generally less, even though the height of the wall is more. You might have seen this. So there are some innovative retaining walls generally done on the say bridges, which may be 9 meters, 10 meters, 8 meters like this, or even more than that, like dam kind of. Okay. Okay.
Okay.
Okay. So thank you all.
Thank you, sir.
हेलो
हाँ, hello.
सर इस बोलना था कि इसको मैनुअल ही करना पड़ेगा, डिजाइन पूरा प्रोसेस मैनुअल ही करना पड़ेगा कि एक्सेल के थ्रू?
एक्सेल में अभी नहीं दूंगा, देने वाला हूं मैं, बट आफ्टर सम टाइम, नॉट नाउ. आई विल गिव यू, बिकॉज क्या होता है एक्सेल दे दिया ना तो लोग कुछ मैन्युअली करते ही नहीं. तो सो आई वुड सजेस्ट कि मुझे दिखाओ मेरे तुम 2 रिटेनिंग वॉल हाथ से किया है, देन आई विल शेयर विथ यू. सी हमारे पास सब है, लेकिन गो विद द प्रोसेस. ओके.
ओके सर।
Yes,
नहीं
sir.
तो क्या होता है ये स्किप कर दोगे, थोड़ा सा कैलकुलेशन किया तो शेयर चाहिए कि वो सब हो जाएगा ना, हाथ से जाएगा। सी अंडरस्टैंडिंग डेवलप होने के बाद वी कैन यूज एनी सॉफ्टवेयर एंड एनी शॉर्टकट्स, आई विल टेल यू दैट। So
Okay.
follow this, show me the calculations, I will give you the Excel. Okay,
Okay, sir.
thank you.
Thank you. Sir, this will be shared ना?
Yes, you will get that in the classroom. आपको
Okay,
क्या
okay.
मतलब PPT क्या ये
Yes,
वाला
yes.
ना? हाँ
हाँ.
yes करेंगे क्लासरूम में रहेगा।
Okay, sir. Okay.
या
Sir,
हाँ
Thank
yes
you.
समीर
Good night.
समीर
सर क्लासेस के रिगार्डिंग पूछना है सर, अब और कितनी क्लासेस लेफ्ट मतलब बची हुई हैं सर अभी?
सी अभी ये सी तुम्हारा तो ऑलरेडी हुआ है ना ट्रेनिंग प्रो कोर्स। हेलो
Yes, sir.
कहाँ गए समीर?
यस सर,
हाँ क्लासेस तुम्हारे तो ऑलरेडी हो चुके हैं ना।
यस सर, यस सर।
नहीं ये अभी बीच बीच में वर्कशॉप्स और रहेंगे, मतलब सी ये ऑप्शनल है लेकिन कंटिन्यूस है ये, मतलब क्या बोल सकते हैं अभी। सी नॉलेज मैं क्या कर रहा हूँ, जो ऑलरेडी एडमिटेड स्टूडेंट्स है ना, जिन्होंने ऑलरेडी लिया है
यस
उनके
सर,
लिए ये बीच बीच में हमारे वर्कशॉप या ऐसी छोटे मोटे सेशंस रहेंगे तो हम इनवाइट तो करने वाले एज पर योर टाइम यू कैन ज्वाइन।
सही है सर, वो चीज सही है सर।
क्योंकि क्या अभी आप यू आर ऑल्सो मे बी वर्किंग बट यू मे बी फाइंडिंग डिफिकल्टी, तो इंटरेक्शन हो जाएगा, थोड़ा एडिशनल नॉलेज मिलता जाएगा, तो
यस
इट्स अ
सर,
कंटिन्यूस प्रोसेस।
नहीं
So
सर,
we will- हाँ बोलिए।
वर्किंग नहीं है सर, हम जॉब आपके जॉब के लिए आप ही को कॉल
नहीं
करने वाले थे।
नहीं वो ठीक है, जो वर्किंग है या नहीं है, मतलब क्लास तो हुआ है ना सबका,
हाँ
बहुत लोगों
क्लास
का,
हुआ है सर।
तो फिर भी वो सीखने का है हमें एडिशनली, क्योंकि ये स्ट्रक्चर इंजीनियरिंग या एनी फील्ड लर्निंग तो कंटिन्यूस करना ही चाहिए।
यस सर।
आगे आगे जाएंगे तो कॉन्फिडेंस और ज्यादा बढ़ेगा एंड देन यू कैन बिकम इंडिविजुअल एक्सपर्ट ऑल्सो ना, क्योंकि क्या क्यों सीखना चाहिए, बिकॉज एक्सपर्ट लेवल तक जाने के लिए करना पड़ता है सब। सी देर इज अ फर्स्ट केस कि लोग बोलते कि मुझे जॉब अच्छा मिलना चाहिए उसके लिए करना है। सेकंड केस रहती कि मुझे बहुत स्ट्रक्चर इंजीनियरिंग में बड़ा बनना है, एक्सपर्ट बनना है, तो ऐसे दो फेजेस में जाना है आपको। ओके
यस सर।
सो थैंक
Thank you, sir.
यू
Thank
एंड
you,
गुड नाइट टू ऑल।
गुड नाइट
गुड
सर।
नाइट सर।
Hello.
हाँ हाँ बोलिए। हेलो
हाँ सर, जो ब्रिज का जो वॉल रहता है सर, वो प्रीकास्ट के पैनल्स लगाते हैं, तो वहाँ पे प्रेशर कैसे सस्टेन होता है? जो
बीच का
ब्रिजेस है
मतलब
सर, ब्रिजेस के जो रिटेनिंग वॉल्स है सर,
हम्म।
उसमें सर प्रीकास्ट के पैनल्स लगाते हैं,
हाँ हाँ हाँ
तो वहां से थ्रस्ट सस्टेन होता है, तो
अंदर
वहाँ
हाँ अंदर
हाँ।
वो स्टील के रॉड्स लगाते हैं उसको पैनल।
सिर्फ पैनल सर एक दूसरे में फंसा रहता है, और हाइट तो सर करीब 6 मीटर 8 मीटर रहती है।
नहीं वो क्या बोलते हैं उसको,
RE
टेंशन
walls.
हाँ टेंशन रॉड्स उसको लगाते हैं, पीछे खींचता है वो, बाहर नहीं निकलता वो। मतलब हॉरिजॉन्टल जो फोर्स आएगा ना
हाँ सर।
उसको क्या बोलते हैं, रॉड्स है ना, स्टील के रॉड्स रहते हैं यहाँ से वहां तक दोनों साइड में, ब्रिज में दोनों साइड में रिटेनिंग वॉल रहती है ना।
हाँ सर।
YouTube पे वीडियो देख सकते हैं आप।
हाँ वहाँ यूट्यूब पे भी है, और वहां वो रॉड लगा रहता है, तो इसकी वजह से वो रॉड में टेंशन आता है। व्हेनेवर देयर इज अ हॉरिजॉन्टल फोर्स ऑन दैट पैनल,
हाँ
the
सर।
rod will try to have a tension, मतलब elongate होगा, and that lateral stability or that pressure is resisted by that tension in the rod।
ओके ओके सर,
ऐसे रहते हैं। हाँ
थैंक यू सर।
थैंक यू।